I tried to make a circuit of a 1970s book with the 555 chip. That chip is enormous popular on the World Wide Web. You can find, say, thousands, I think thousands of electronic circuits with that chip. But the circuit out of 1973 or so didn't work, so I had to go back to my linear data book that is always reliable, and I made it according to this schematic as an A-stable multivibrator. I did some changes, but of course no real changes, because you have to follow, of course, the description of this chip, etc, etc. So this was finally my circuit and setup. I've drawn it in another way compared to the book, though of course I refer to the original schematic from the National Semiconductors book, and I wanted to make an oscillator that works with a variable duty cycle, and that is, say, the most important thing here. I made it in this way on a piece of wood with brass nails, and for the higher frequencies I think this is not a good idea, because I have a more or less bad waveform. I want to show that. So when you want to make it in a more stable way, make it in the Manhattan style on a copper clad board with a good ground plane, etc, etc. But for lower frequencies, say up to 3 kHz, you can surely make it in this way, like I made it. So we are now on 49 Hertz, and this is a waveform. By the way, I could not succeed in getting here pure 50-50 duty cycle, and you can do that, find that out by experimenting with this resistor here. There are two of them, 82 kilo ohm and 27 kilo ohm, and here's the duty cycle. I will tell more about it. So when you do some changes here in this range, of course they are paralleled. So use the standard formulas for parallel resistors, and here you can set that duty cycle. Wanna do that now? I have to find at first a screwdriver to do that. Take some time, sorry for that. So now I'm changing here the duty cycle with the help of this potentiometer here, and let's see what happens. That's of course very important. So let's see, we are on the 50 Hertz frequency, and I'm changing it now to this. I think I do better to switch out all the lights. So here is the duty cycle is changed, the frequency also changes, and now we are on 82 Hertz. Turn the potmeter back, and I've chosen, say, values via which you can get to the, in my opinion, best duty cycle possible with this circuit. And you can surely see it here. Here there is a smaller time, here a somewhat longer time, and that's the reason why in the schematic I have told that there is a 20% deviation anyway. So what more to tell? This is perhaps an important table. Here are all the the frequencies that you can make with the circuit by changing here this capacitor frequency Cx. That's the capacitor that is responsible for the frequency where it works. And with these values you get a more or less 50-50 duty cycle. Like I told, I couldn't get it better, so I tell here 20% deviation. But anyway, 1 microfarad you are on 10 Hertz, 0.47 microfarad 20 Hertz, 0.33 microfarad 3 Hertz, etc, etc. And I have to say that on the highest frequencies, say around 4 kilocycles and 14 kilocycles, when that timing capacitor is 1 nanofarad or 3300 picofarad, the waveform is, in my opinion, not okay. I want to demonstrate that there is here now a 1 nanofarad cap, and I remove now the parallel cap. And now we are, say, on the highest frequency that this can give 14 kilohertz. You can even go higher because when you don't connect a timer capacitor, it also oscillates. The 555 also oscillates without a capacitor. Perhaps I can demonstrate it when I have time. So here is that 14 kilohertz. I have to, so, well, you can see big peaks here. But anyway, waveform is quite good. Let me turn that duty cycle pot meter again. So here, very strange, by the way, 13 kilohertz now, and well, here. So here there is a kind of equilibrium. That's not bad, by the way. That's 14 kilohertz. So anyway, well, that was more or less all to tell. Again, the schematic for the best overview. And here you see, say, depending on each capacitor value, the range, when you turn that duty cycle potentiometer. So 10 to 17 Hertz, 49 to 82, 1.1 to 1.4 kilocycles in that case. Well, finally, let me try to cut out the timer capacitor. Perhaps that's a good idea to show that even, so now there is no timer capacitor here in the circuit. Now even in this case you have an oscillation. That could also be, say, helpful for experiments with oscillators, say driver circuits, drivers of transistors on higher frequencies, etc, etc. The peaks here could be caused, like I told, by the way that I made the circuit, and we are on 50 kilohertz. That's quite high. Thanks for watching.